No.
We get to play with dangerous chemicals today.
Isn't it like salt?
I don't care, I just want to blow something up. Promise nothing's gonna blow up this time.
No.
No, she doesn't promise. It's chemistry, you know it's
Okay, like the hydrogen balloon and the sodium. I'm just
Oh.
waiting for a third explosion to happen, that's all I'm saying.
Is that a challenge?
Yes.
Yeah, yes. It's like we can.
What have I done?
Something great.
Explosions are great.
I'll provide the key. Costco also sell giant chunks of soda.
I wish.
Yeah, they should have a Costco chemistry.
Oh gosh.
You have everything you need to blow up your market.
You just have to show you have like a minor in chemistry.
Oh
Or
gosh.
at least, that's like the lowest qualification.
That'd be pretty funny.
Instead of a Costco membership, that's like to show.
All right, so let's see if we can warm up with what we had been talking about. So remember, we were looking at freezing point depression, and we looked at this KF factor and calculated that. And so then we said, okay, well now let's look at boiling. And so like we had mentioned the last time, now we have boiling point elevation, and again thinking about adding a solid to that. And again, same thing, we have a proportionality constant. So now KB, so B for boiling. And let's look at the graph before we do the math. And again, so we have our graph here of our pure solvent versus our solution. And now we can see there's our boiling point elevation as our curve has changed, right, from our blue line to our red line. So now let's see if we can do the math for the boiling point. And let's get some values for you. So it says what mass of ethylene glycol, and it gives you the formula C2H6O2 in grams must you add to 1 kilogram of water to produce a solution that boils at 105 degrees Celsius. And it gives you a hint that the change in boiling point is 5 degrees. So then we can look at our water, and you need your KB constant, so 0.512. So KB H2O. And again, unit on those is degrees Celsius per molality. Sorry, let me rewrite that. So see if you can figure this problem out now. So how's this problem going? So do we have our setup? Because this is a little different, right, than our previous one that we finished on Monday. So, right, if we kind of look back to the one we did on Monday, okay, we had the KF times the molality gives us a change in temperature. And so if we look at what they're asking us to do today, well, this time they've already given us the change in temperature, right? So we have our delta T, so that's 5 degrees Celsius. But then we're actually trying to solve for, right, the molality first. So first we actually have to get molality, right, and then from there we can answer the mass question. So then let's plug it in to our formula. So delta T is equal to KB times our molality. And so then we get 5 degrees Celsius is equal to 0.512 for our KB times X here, since again trying to figure out molality. So now 5 divided by 0.512. So we should have a molality of 9.76 little m. And remember, molality is moles over kilogram. So you can always go back. Where was it? So right, this page is good to have handy for your notes. Okay, molality, moles, kilograms. All right. And so now that we have our molality, now we can figure the rest of this out. So we have 1 kilogram. So that means we need 9.76 moles of ethylene glycol. And then we just have to calculate our molecular weight of ethylene glycol. Did anybody do that? So 12 times 2 plus 1.008 times 6 plus 15.99 times 2. So 62.07 you said? And that's what chat has as well. Let's go with that. So molecular weight 62.07 grams per mole for ethylene glycol. And so now we need to multiply it. So times 9.76 moles. So pretty large. So we need 605, and then let me check sig figs. It looks like we only had 1 there actually. So 6.0 times, or we could round. So 610 then, roughly, grams of ethylene glycol. So you want to do another practice like that? Yeah, so let's do another practice problem. Here, let's look at another one. I'm going to insert a practice problem here so we can look at the chart. So now let's practice. So 5 grams of sodium chloride are added to 500 milliliters of carbon tetrachloride. So what is the new freezing point? And you probably need one other little bit of information. And so you need that the density of carbon tetrachloride is 1.59 grams per milliliter. So that will help you. So what are we thinking with this one? Because there's a few little bits of information that we have to calculate before we just plug it into our formula. Yeah, so how do we get molality? And let's think about that for a second, right? So, okay, remind yourself what molality is. So molality is moles over kilograms of solvent. So how do we get, so now we have to really figure out two pieces, right? Because we have to get moles of our sodium chloride, so we need to calculate that. And then I was kind of tricky with y'all, right? And I didn't give you kilograms of solvent. I gave you milliliters. And then we weren't working with water. So now we have to take into account the density. So let's go through that. So let's just do the sodium chloride first, so finding moles of that, because that'll probably be a little bit more straightforward. So find moles of sodium chloride. So we can take our 5 grams and then, remind me, what's the molecular weight of sodium chloride again? It's like 55 point. Oh, 58, I could be wrong. 58.45 maybe?
Let me double check. 58.4.
Okay, so about 58.4 grams per mole. All right, so then we have our moles of sodium chloride. And then, so looking at the chat, right, we don't need the molecular weight of our carbon tetrachloride, because all we need is a total kilogram of the solvent, right? Again, looking back at the definition of molality. And so let's go ahead.
Would you just use like the conversion factor times it?
Yeah, so, right, use your units to help you. So I think that's what you're saying, right? So you have 500 milliliters. And then it's grams per milliliter, right? So we're seeing, okay, we can just multiply them, right? And get our total mass. So now let's do that. And that's good, right? So that's kind of the what you should be getting from this chapter is, again, there's a lot of different units. We're seeing that, but that's where your dimensional analysis helps you. So that's good. So now find kilogram of solvent. So we'll start with 500 milliliters multiplied by our densities, so 1.59. Again, that's grams per milliliter, so we'll have to do some converting. So now that's in grams. So divided by 1,000 to give me kilograms, so 0.759 kilograms. So now we can actually calculate our molality. So we're getting to our home stretch, right? We have moles, we have kilograms. Now we can find our molality. So now molality. I'm just rewriting the definition. So now we can plug in our numbers that we found. So moles of sodium chloride over total kilograms of solvent. Trying not to round till the end. All right, so now that's our molality. So 0.10. Wait, you got stuck there? That's everything else I thought was the harder part. So once we have our molality, now we can go back to this chart here, right? So now we have to look, okay, for carbon tetrachloride, the freezing point is given as negative 22.9. The KF for freezing, again, because we're talking about freezing point, is 29.9. So now we can plug it in to our formula. So our change in temperature is going to be equal to, again, KF times molality. So then that's equal to our, again, 29.9 then, times our molality that we found. Oops. And so then we get a change in temperature of 3 degrees. And then remember, freezing point depression. So it's going to lower it. So 3.22. So freezing point depression, so we know we need to subtract it. So now we take our original freezing point, so negative 22.9 minus this new one, so giving us a new freezing point of negative 26.1 or so. That-
I was confused on the original freezing.
Oh,
point.
yeah.
And I was like, what am I?
Yeah, because once you find the change, then it might ask, yeah, what's the new one? And so again, right, you'd have to be given all these values. You have to be given your KF or whatever solvent. So hopefully, again, that kind of helps push you in the right direction.
So in the first problem we did, we looked at water's freezing point because it was in an aqueous solution, correct?
Yeah, exactly.
And then if we're not looking at water, he would give us the density of what we're looking at?
Yeah.
Okay.
Yeah, so I'll have to give you the density of everything else. So all of these have different densities, less than 1. So yeah. All right, let's finish up, I guess, the last bit of lecture, and then we'll do the demo that will help us remember electrolytes and weak acids and bases. And so osmosis is just defined as a flow of solvent from a solution of low concentration into a solution of high concentration. And so this is usually water, right, that's flowing. And so usually the idea is that it's trying to get the same concentration on each side. So that's thermodynamically favorable. And so, of course, in order for this flow to happen, there has to be some sort of semi-permeable membrane that may allow solvent to flow through, again, such as water. And so looking at this little diagram, so they're showing us all these water molecules. So on the left side, there's more water molecules. And then on, oh, I screwed that up. So on the right side, right, there's only water molecules. And then on the left side, there's the addition of these solute particles being dissolved. And then, so to achieve equilibrium, the water is going to flow from the right side to the left side to equilibrate that osmotic pressure. And so that's what's being measured here. So this rise in the fluid then is then equal to the osmotic pressure of the solution. And so, well, what is that? And so we can look at it. We don't really use this formula too much in this class, so we can just kind of appreciate it, that our osmotic pressure is related to the molarity, so big M times our gas constant times RT here. So we can see that. But what we really want to look at too and understand, and this comes up in your homework, is we want to see, well, how many particles actually dissolve? Because that's what our factor is here. And so let's look at that. So sometimes you might see this formula with a little I here. So that's our Van Hoff factor. And well, let's look at that. And so the Van Hoff factor is just saying how many electrolytes are we expecting to make in solution. And so kind of how to think about this is, okay, well, it starts you off with a non-electrolyte, like sugar, right? So we're saying, well, if we have 1 molar concentration of sugar in solution, right, we're going to have 1 molar of sugar still, right? So obviously it's a non-electrolyte, so it doesn't disassociate, so we still have 1 molar of particles. So if we go down to sodium chloride, so now it has a little factor of 2, and okay, well, let's think about that. So if we have a 1 molar sodium chloride solution, right, it disassociates into 1 molar of sodium ions plus 1 molar concentration of chloride, so giving us, right, 2 molar effective of ions in solution. So you have more ions. And so then if we compare that, so now magnesium sulfate, and then for our purposes, we're just going to go with the expected, right? So obviously there's some sort of, you know, it's not perfectly disassociated or whatever. I'm not quite sure, you know, how this is calculated and measured, but, you know, we're not going to worry about that. So again, magnesium sulfate, if we have 1 molar solution of that, we're assuming it fully disassociates. So we have 1 mole of magnesium, 1 molar solution of magnesium ions, plus our 1 molar solution of sulfate. Again, giving us effectively 2 molar of ions. And sometimes you do see this as normality. So normality, not to get too off subject, but this is like the measure of ions. So that's sometimes where you see it. It's just, we don't usually use normality, but I've noticed, like, I only know this because some guy wanted to take my class, but then he never did. But over at Ericsson, you know, that company with airplanes, they do like a bunch of like metallurgy, metal plating. So they use a bunch of normality units, which is just kind of funny because they didn't know what those units meant, but that's what it's related to. But anyways, just kind of a fact if you ever see that. And then, so looking at these other examples, so we have magnesium chloride. So again, if we have 1 mole of magnesium chloride, right, we're getting 1 equivalent of magnesium, and then 2 of chloride to give us, right, 3 molar solution of ions. And then blah, blah, blah. So last one there, we'll just skip down to iron chloride. So again, we have a 1 molar solution of it, but then it makes 1 mole of iron 3+, and then 3 molar solution of chloride ions, so giving us, right, 4 molar of ions effectively. And so we'll revisit this in a second because we'll look at the homework and where this applies. And so then last little bit, we should just go over these terms. And so these are also used in, you know, medical terminology, in biology.
Yeah, I'm in my class. I'm in terminology.
Oh, have you talked about all these osmotic, isotonic?
No, we haven't gotten to that part yet.
Well, yeah, I'm sure you'll talk about it. So, right, you have isoosmotic, or also known as isotonic. And so that just means the same osmotic pressure. So, right, you have the same concentration of ions in and outside of the cell. And so there's no net flow of water then in or out. So that being said, right, there's still an exchange, but it's not going, you know, one way over the other. And so now let's look at a hyperosmotic solution, or a hypertonic solution. And so this could be, you know, maybe if you have a too high sodium of a diet, obviously, right, this is a very extreme case, right, but this just kind of gives you a sense of why you don't want to put too many electrolytes in your bloodstream. although now I've been hearing research that now we have too few electrolytes, so who knows. But essentially, right, again, if you were to way overdo it, let's just say with the salt, then potentially, right, your cells are going to lose water as you're trying to equilibrate all the extra salt that's floating around in your blood. And of course, that would leave your poor cells a little shriveled and dehydrated. And then we have a hypoosmotic, so hypo being lower, or hypotonic. So again, your solution has a lower osmotic pressure than the solution in the cell, so fewer ions. And so that means, right, the water is going to flow into the cell to, again, try to equilibrate for that. So now you can understand why those gallon challenges could potentially be dangerous, right, that people like to do, where you chug a gallon of water or something. And again, right, it depends on every person and their body and blah, blah, blah. But essentially what could happen, in theory, is, again, you have too much water. So now you've diluted down your blood a little bit too much, right? And then that could cause some damage, again, by the water trying to go into the cell, and then eventually causing it to burst. All right, so let's look at our demo here. Let me pop this out too. So y'all can see it. Oh. Yeah, exactly. So the chat mentioned that, yeah, so it can make your brain swell. So same thing, right? So all your cells in your brain. So exactly, right? That's why you're going to have brain swelling with your cells because of that. All right, still trying to get our camera work going. All right, there we go. And so we just want to look at these electrolyte solutions then. And so actually, before we get to the demo, let's kind of recap real quick. Well, what were we talking about? So, right, we were looking at these electrolyte solutions. And so we had said, right, an electrolyte is something that disassociates into ions and conducts electricity. And we also mentioned this concept, right, of our weak acids and bases, that they have some sort of equilibrium. And so let's look at that. I was just saying, so there's more electrolytes. So I was looking for this picture because now we're essentially going to do this, but more of them. Oops, and I had the wrong. So sorry for your online folks. So just going back to our electrolyte slide, okay, reminding ourselves. Let's go back to our demo. All right, so let me get set up here. I don't know how my extension cord gets to. All right, so we have our setup here. So we have our light bulb before I hook it in. So right, light bulb, and then obviously, so it's not hooked in right now, but we're going to complete the circuit. And so, right, safety tips, you don't want to take both hands and complete the circuit like that, obviously, with your body, since you don't want it to run across your heart. So ideally, you want to hold it with just one hand. Just kind of making sure, yeah, everything's in the frame. Okay, so now let's test this. And so we'll start off with just water. So I have plain water here. Let me just rinse this one more time, make sure it's nice and clean. All right, so let's dip it in our water. And nothing happens. right? So we expect that so that it's distilled water. So sometimes if you use your tap water from your sink, you can get it to light up. And so now let's compare that to salt, right?
The tap water, because there's still.
Yeah, like if there's enough ions.
So,
and-
what about like well water and stuff?
Um,
Probably light up a lot more.
Yeah, if we really wanted, the stockroom might have some well water
I
that we
could bring
could try.
some.
Yeah, if you want to bring
Okay.
well water,
I'll put some in a mason jar.
yeah, that'd be fun.
That makes you wonder, why don't we just use salt water as like an alternative energy source if it can, produce
Well,
some
it's-
form of electricity?
Well, all it's doing is completing the circuit, right? So it's not producing electricity, so that would be like a galvanic cell. All it's doing, right, is completing our circuit from so we're just getting the electricity right from our normal light bulb source. All right, so that was salt water. And then let's compare that to a non-electrolyte next. So, okay, sugar, and you can tell by the huge clump of sugar. So I really tried to put a ton of sugar in there to make the point. And yes, right, I put a shit ton of sugar, and it doesn't matter. Still doesn't light up. So not an electrolyte, right? Not making ions.
Is it homogeneous or heterogeneous since it's not fully dissolving?
Yeah, so that would be a heterogeneous solution.
So, but if the water was warmer, it would be homogeneous.
Yeah, so we
With
could-
the salt, you could manipulate it. But
Yeah, so we could get like a simple sugar syrup, right? We could heat it up, make it super saturated, but that wouldn't help us conducting the light bulb. All right, so now let's do the acids. I just didn't want to pour them out. So we'll compare. So I got 4 molar acetic acid, and then we want to compare that with how bright it is compared to, I have 4 molar sodium hydroxide, and then we didn't have quite the equivalent prepared in the stockroom, so I just went with the 3 molar acid, so hydrochloric, so again we can compare the strong and the weak acids. So again, the key point of the weak acid is that it's not fully disassociated. So now if we put it in, and so look how weak it lights up, right? So that's 4 molar acetic acid, but again, because not all of it is disassociated, we have this really weak light bulb. And so now let me clean that a little so I don't do an acid-base reaction.
What happens when you combine the acids? I mean, on accident, I mean.
Nothing if you do acetic and hydrochloric, really. But I just don't want to mix acetic. And so now compare how much brighter that is. So again, same molarity. So if they had been fully disassociated, right, they should have been the same brightness. But obviously, since sodium hydroxide is a strong base, that lit up more. So again, right, it's fully disassociated. And then let's just compare that to the HCl. So like I said, it's a little bit weaker, so 3 molar, but let's just see, so right, lights up that light bulb, again, super brightly, since it's fully disassociated. That was fun. So I can leave this up here, if you all kind of want to play with it. I'll just unplug it at least so that we don't accidentally shock ourselves, All right, so that was, again, just that recapping. Again, our non-electrolyte versus weak versus the strong, fully disassociated.
And all acids and bases are electrolytes.
Yeah, so yeah, that's a good recap, right? So all acids and bases are electrolytes. It's just a question of, is it, strong or weak? And so, right, we've mentioned HCl was strong because it fully disassociated. We talked about our acetic acid that we worked
And
with.
this is all based on hydrogen bonding, basically, right? These
Somewhat,
are
yeah.
measured by like strong acids and bases.
Yeah, well,
Right.
technically, and we'll get into this next week, but we're measuring the hydronium concentration.
Okay.
So that's what it's related to, is the concentration of H+ ions.
Okay.
So with these, you have to calculate, you know, so it's just like a certain percentage is in
So, like,
solution.
like when you're doing a chemical reaction, like does some of the hydrogen stay with the original, or does it all be transferred?
So that it kind of depends. So it's more of like a reaction, so that like usually you have to kind of analyze it, right? So because it also depends like if there's a buffer too. So like you kind of saw that today.
Right.
So if you have like acetic acid and acetate, you kind of have to do the neutralization reaction, but then see if it's going to kind of reform anything. So yeah, but I mean, you're kind of getting the idea, right? It's like back and forth. And yeah, I mean, it's supposed to be. That's the beauty of it. And then, yeah, just kind of recapping. So I was going to say, I can't think of any weak bases. The one that I should think of, though, is ammonia. So that's, right, the weak base that we see. Otherwise, most of them tend to be strong, right, if they're based off of the hydroxide. I should put weak. All right, let's do some practice now. So we pretty much covered the chapter. I think we only have 10 minutes, since I promised I would let y'all enjoy your Thanksgiving. And so let's try, actually let's skip that one for now. Let's look at these solution ones, because this is related to that Van Hoff factor. So take a minute to look at this, and then we'll go over what the hint is. Yeah. Yeah, so that's the trick here. So let's go over that now, right? So then it's talking about particles in quote here, but what it's trying to get you to think of is, yeah, that Van Hoff factor. And so all you need to do is then kind of figure out, well, what's my true molarity? And so sucrose, though, well, does sucrose dissociate? So no, okay, it's a non-electrolyte, so it's still 0.1 molar, that's fine. But what about sodium chloride? What's its effective molarity? 0.16. So 0.16 molarity, exactly, so times 2, right, for 2 particles. And then what about magnesium chloride? So how many particles? 0.09. So 0.09, right? So magnesium chloride, so times 3. So 0.09 for the effective molarity. And so now you just have to order them. And I think that's the hardest part, is just understanding their true molarity. And then, so now we can do the first one, so increasing vapor pressure, right? And so now more particles decrease the vapor pressure. So which one has the highest vapor pressure? So magnesium chloride, since it's the lowest. And then, right, now we can order them. So sucrose is in the middle, since it's right the middle molarity, and then sodium chloride would have the lowest vapor pressure, highest boiling point. And so then, right, you kind of repeat that, so boiling point, elevation. So now it's going to be, right, the opposite. So sodium chloride's the highest one, sucrose is in the middle, magnesium chloride, so etc. So let's look at the other one. So I'll let you figure out the rest now that we have the ordering. But let's look at kind of these first ones up there, because these could get tricky. And so now let's see if you can calculate the molarity of our solution 1. So 10 grams of naphthalene and 500 milliliters of chloroform. And then just compare that, right, to the weight per volume concentration. So let's look at a few of these. I know we're running out of time here. And so how would we approach number 2 with finding our molarities? So what do we need to do? So moles of naphthalene. So take our 10 grams divided by the molecular weight, which I cheated and looked up today. I was too lazy. So 128.174 is what Wikipedia is telling me. And of course, right, we could have added it up. I'm just trying to do it quickly here. We're running out of time. So now we have our moles. And so what do we do after we find our moles?
Find the kilograms of solvent.
Not kilograms, because remember it's molarity. Yeah, liters. So that is like the biggest thing, right? Just and I don't know like who invented it, like who did.
Molarity versus molarity.
Yeah, like it's
And
horrible
like
naming.
one tiny difference.
Exactly. So that's like my biggest warning is just be careful in looking at molarity versus molality. So yeah, it's moles over liters.
What is that word next to moles?
What, the arrow?
No,
Naphthalene?
naphthalene? Naphthalene?
Yeah. So then divided by our liters, so we're given 500 milliliters, so divided by 0.5. So then we get our molarity of 0.156.
And molarity is capital M.
Yes, so big, capital M,
And molality is lower.
yeah, and the molality is lowercase, which, not to be confused with anything else that starts with a little m.
Yeah, what if your little m and your big M look exactly alike?
Sorry, I think I missed it. Where'd the point five come from?
Oh, just the 500 milliliters, so we converted that
Oh,
to 0.5 liters. Yeah. And then we're out of and over time, but I just want to point out, right, again, just read these, because then it's just asking weight per volume. So, right, we can literally just take 10 grams over 500 milliliters, right, and that is our answer there for that second one. So then let's just plug it in, right, 10 divided by 500. So, and then multiply by 100 because they want percent. And so, okay, that gives us, right, a 2%. And then you can see that W per V, so weight per volume. And so that's all, right? So again, don't overthink these things. Just show your work. And then so for some of these, I might also suggest using proportions. So that might be helpful to some people. And we can also talk about that individually. So I'll probably be ending lecture pretty shortly, but right, I'll still hang around for office hours basically as long as y'all are here. But I know people have plans and probably want to get going. But yeah, that's all I have to say is emphasize, read everything. You got your C1, V1, C2, V2. So not too bad this quarter. All right, I'll let people slip out. I know people's got things to do and families to see.
So we need to make a little cheat sheet of all the different formulas.
Yeah, I mean, like honestly, where was that sheet again? Like,
The one about the different concentration ones.
yeah, like the little summary chart. Obviously, I can't find it. But yeah, I feel like you should just print that out.
Yeah.
Yeah, that one. Just like, print it out, have it there, because you just need your little cheat sheet to help you. But yeah. Happy Thanksgiving. Have a good one, everybody. Be safe. All right, I'll hang around on stream just in case there's any last few questions, but like I put, there's no quiz today, so that's my Thanksgiving gift to you. And yeah, go home, eat turkey. Oh, yeah, that's fine. I like your shirt, by the way. And your pants are funny, too.
Yeah, my daughter got sick overnight, like super sick, so I called in this morning. So I was already gonna do a half day today, and I was like, screw it. So I'm just in my full form as I am at home.
All right, I'll end the stream, and then you can always catch me on Zoom as well. Even this weekend, I'll be watching my emails just in case. All right, thanks again. I'm going to end our stream officially.